Hello. Welcome to my new video on Mini Smart Home System with W5100S EVB Pico 2. This video is an updated version of my previous project, where I created the Android app that controls our W5100S board. In this updated version, you'll be able to turn on the fan when the temperature reaches a certain value, which currently is set to 25 degrees Celsius. Also, in this updated version, you'll be able to adjust the brightness of the LED strip on this box. By changing the seek bar component of the app, you can now control the brightness of the light when you press the toggle button on the tablet. In this video, I will start by talking about the needed components, then the hardware connections, and lastly the codes on CircutiPython and Android Studio. You can find related links down in the description below. Now, let's start the video. You will need the following hardware components in the updated system. For the fan section, you will need the fan, a power supply, and a relay module. The fan model used here is produced by Minebea Motor, and it runs on 12 volt under 2 wires. To match the required voltage for the fan, I used the XY SK35 power supply, which can output up to 24 volts to run the fan. Lastly, we will need to use a relay module to connect the power supply, the fan, and the Pico 2 board. Basically, the relay module is used to allow a low-power control signal to activate or deactivate an isolated higher power circuit, which is very common in automations. For the box with light strips, you will need a separated USB to micro USB cable and the N-Channel MOSFET Module, so that our board can change the brightness of the light. Likewise, the N-Channel MOSFET Module also allows a low-power control signal to control a higher power circuit, but it does not isolate both of the circuits. One advantage of using it is that it provides a much faster on or off speed, allowing applications such as PWM. Next, I will talk about how to connect these components together with our Pico 2 board. Let's start with the fan first. I followed this guide on YouTube to learn about using relays with the Pico board. From these animations from buildelectroniccircuit.com, the ground wire of the component is connected to the normally open port of the relay, which means that the right side circuit is open in its default state, and once our left side circuit energizes the relay, the right circuit becomes connected, which turns on the AC lamp. Vice versa, if we connect the ground wire of the component to the normally closed port, the default state of the light is on as the circuit is closed, and once the left circuit triggers the relay, the right circuit will become open, which turns off the light. Following the YouTube guide by Core Electronics, we also connect the ground wire of our fan to the COM port of the relay. You would also need to connect the positive terminal of the power supply to the positive wire of the fan. As in this project, I want my default state of the fan to be off, so I will connect the negative port of the power supply to the normally open port of the relay. This is how I connect these components in my current setup. For the board-to-relay circuit, I bind the signal pin to GP9 of the Pico 2 board. Next, you will need the following procedure for the light box. First, splice a USB to micro USB wire and remove some of the plastic coating of the copper wire at the tip of the separated section using a wire stripper. With the two wires with a USB head and a micro USB head, you can now insert the USB cable wire to the input voltage of the MOSFET module and the micro USB wire to the output voltage ports. Lastly, connect this module with the board. You can connect any of the 3 pins at the top with any available GPIO pin, as the ports are all used for PWM, and the bottom 3 pins are used for ground. This completes the connection of the light box. You can also try the connection with other hardware components. Let's move on to the coding section now. In this section, we will be using the codes from our previous project and add these new features accordingly. As we will be using Adafruit as our IoT platform during cloud mode, we will need to add 2 more feeds for fan and the lightbox so that our microcontroller server and our Android app can reference these values and act accordingly. I will first talk about the fan and lightbox code on CircutiPython, then we will move on to the Kotlin codes. Firstly, initialize the fan as follows. Set the value to false to initialize the default state of the fan to be off. Next, we need to change the SFA30 endpoint of the HTTP server. In the previous version, the SFA30 only functions whenever I call to this SFA30 endpoint. During my implementation of the fan, I find it better for the SFA30 to record the data on every loop instead of recording data whenever the app calls to this endpoint. Therefore, I move the SFA30 algorithm to a function that will be called every loop, use a variable to store the temperature of the SFA30 output, and on every loop, this variable will be checked, and depending on the threshold, the fan will be turned on or off. Since now the SFA30 will be ran outside of the SFA30 route, we remove the algorithm and simply return a JSON response according to the readings. I have also added the fan value to the JSON response so that the app knows the state of the fan and change the image on the app accordingly. After that, for Adafruit mode, we first define the feed for the fan and subscribe to the feed. Then, we will post the fan value to the feed in the first iteration when the server runs in cloud mode. Before entering cloud mode, increase the throttle interval to Adafruit so you send fewer updates to the feeds and avoid being rate limited. Inside the cloud mode loop, I first check if the temperature is above the threshold and the fan is off. If this condition is fulfilled, I turn the fan on and publish its new state. Likewise, if the temperature is below the threshold and the fan is on, I turn it off and publish the new state. For the other cases, I skip publishing since the fan's state hasn't changed. Lastly, update the fan feed to its default value when we turn off the device. Next, we need to import PWM out from PWM-IO and configure your GPIO pin as a PWM output to adjust the lightbox brightness. Here you can see I initialized a stored value set as 65535. This is used to set the light to the maximum PWM duty cycle, so whenever the user turns the light on for the first time, it starts at full brightness before any adjustments. Then, whenever the user adjusts the brightness, we update this value so that reopening the light in the same session restores to the last level instead of resetting to the maximum brightness. On a side note, while testing for the lightbox, I hit an all timers used error because I used the same PWM slice, but different channel for the MP3 sound output located at GP26 from my previous video and the light output located at GP11. A quick fix for this error is simply use a different PWM slice, so I set the light output at GP12. Next, we need to adjust the light endpoint at the local mode for the device. Upon receiving a request on this route, the server checks the light's duty cycle. If it's 0, it restores the saved brightness. Otherwise, it sets the duty cycle to 0 to turn the light off. Next, we create an endpoint for changing the brightness. Inside it, we scale the brightness from 0 to 100 from the app to the minimum and maximum value of the PWM duty cycle. Save the brightness at last for the light endpoint. For Adafruit mode, we also start with creating the light feed and subscribe to it in the connected function. We would need to adjust the message function as well. In the message function, the light feed refers to the on or off state while the box light feed refers to the brightness. So, we turn on or off the lights whenever we receive updates on the light feed, and if there are updates on the box light feed, we scale and change the duty cycle of the light while stowing the brightness. Also, before entering the MQTT client, publish the light's current state to keep the device and IoT platform in sync when the device enters cloud mode from local mode. Lastly, set the value to off on Adafruit when we stop running our device. The codes on CircutiPython is completed. Now, let's move on to the Kotlin code on Android Studio. Let's start with the activity main XML file. Unlike the previous version, I have added a seek bar, an apply button, and a fan image. This fan icon is an image button that updates live with the IoT device. The reason for it being an image button is that in the future, I may include a new button for auto mode and manual mode so that we can change the fan state in manual mode by pressing this button. The seek bar and the apply button works together, where setting the seek bar value and pressing the apply button changes the PWM duty cycle of the light on our box. Next, let's set the logics behind these components. After setting the slider component and button inside the Kotlin code, I also assigned a variable to capture the seek bar's value on change, and will be sent inside a request when the user pressed apply. For the fan image button, I've disabled it by setting as enabled equals false, as the app currently runs in auto mode only. Next, configure the Adafruit I/O endpoints for our newly added feeds. Inside the discovery job from my previous video, you will need to disable these new components when there is no internet access. After finishing the setups, we can now code the section for data transmission. Firstly, before enabling the apply button, check if the light is on. If it's off, show a message prompting the user to turn it on before adjusting brightness. Here is a demonstration of the upon feature. Next, we reuse the lightbulb button's request logic here to send the HTTP request. If we connect to the board locally, we use HTTP post request to send the seek bar value as string to the Lightbox endpoint. In cloud mode, after verifying the board is online, we post the slider value to the Adafruit Lightbox feed, completing the cloud mode brightness control. This completes the slider and the slider button. We will now code the fan image button component. Recalling from our SFA30 endpoint implementation, I added a new JSON field on the state of the fan. Therefore, we can now set the image of the fan based on this JSON field inside the getData job. To showcase the feature, I've swapped the temperature to a manual button trigger that toggles the fan on or off, and the app instantly follows the device's state. In cloud mode, we copy the async await method for the SFA30 data and change to the fan endpoint. As the value posted to Adafruit is in 1 or 0 instead of Boolean, check with number instead to change the fan image. Lastly, when the IoT device is not online, set the default image to off. This completes all the code on this video. Thanks for watching. I hope by this video you can learn how to use the relay and the MOSFET module alongside hardware that requires more power with our W5100S EVB Pico 2 board. By increasing the number of hardware component to the board, we can slowly transform our board into a personalized mini smart home system with your own app. If you like this video, be sure to like and subscribe to the channel for more related content. Feel free to leave a comment if you have any questions. See you soon.